of foot candles, and P of 2 was 20 milligrams of carbon per cubic meter per hour. Okay, so let's continue with other things. Again, this is basically an algebra situation. It's not really calculus. A farmer has 1,200 feet of fencing for enclosing a trapezoidal field along a river as shown. So these are parallel. This is the height if you want. Big base, small base, height. One of the parallel sides is 3 times longer than the other. So they're giving us x and 3x. No fencing is needed along the river. Find the largest area the farmer can enclose. Again, this is an algebra. If you want to work on it, we can. Okay. A box with an open top is to be constructed from a 4 by 3 rectangular piece of cardboard. Okay, so 4 by 3. Okay, I guess 4 by 3. Okay. By cutting out squares or rectangles from each of the 4 corners. Fine. As shown in the figure, and bending up the sides. One of the longer sides of the box is to have a double layer of cardboard. This piece, which is obtained by folding the side twice. Find the largest volume that such a box can have. So that's an option. A rectangular storage container without a lid is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs, this is more interesting, but it's up to you. So are we interested in 2021 or move on?
Can we do number 20?
Yeah. So let's take a look at number 20. So with number 20, I just need to show what's happening here. So assuming that this is the piece of cardboard. So we are going to fold this for some reason twice. And we're going to remove those corners. And create a box. This is nowhere near a box, but I know you're going to say, okay, she tried to show us a box. Okay? So that's what it is. For some reason, they want this to be folded twice. So not just once, but twice. And this is the box. Okay. Good. So let's copy what they're giving us. So it's a 4 by 3. So this is problem 20. So 4 feet by 3 feet. And here we have, just on this side, we have 2x and x, but everywhere else we have x and x. Okay. So I copy that. So then they say cutting squares, okay, rectangles, 4 corners, as shown in the figure, and bending up, okay, one of the book, which is obtained by folding the sidewise. Fine. Find the largest volume that such a box can have. Uh-oh. So they're asking us to maximize the volume. This is the question here. So find x, because that x is the unknown here, right? So find x such that the volume of this box, which will look like this, is maximum possible. It depends on the restrictions we have, and the restrictions are 4 feet by 3 feet. So we have to identify the length of the box. This is the first thing we need to determine. And we also need to determine the width of the box, because then I can determine the volume. I need this function in order to find its maximum. If I don't have the volume function, then I cannot find its maximum. So let's piece by piece identify what is the width.
Is it 4 feet minus 2x?
Exactly, perfect. So this is the length. 4 minus 2x. Awesome. So this is it right here, 4 minus 2x. And now we have to determine the width. So this was the length, so we want to determine the width. Anyone would like to give it a try? So this is 3. This is 2x. And this is x.
Three minus 3x.
That's it. Oh, 3 minus 3x, of course. Very good, awesome. And now we need to identify the height of the box. Can anyone give us the height of the box?
Wouldn't it just be x?
Of course, thank you very much. Thank you for your contribution. And now can anyone give us the formula for the volume? What should I write?
Isn't it just width times height times
Exactly. Area.
length?
Exactly. Area of the base times the height. This times this times this. X, 4 minus 2x, 3 minus 3x. Excellent. And now I can say this is indeed a function of x only. So I have the volume. And I learned in this chapter what to do to find the maximum. So I need to expand this. And what I would like to do is just keep x alone and just distribute. 12 minus 12x minus 6x plus 6x squared. And then distribute x. So x times 6, so it'll be 6x cubed. This is negative 18, so minus 18x squared and plus 12x. So this is the formula for the volume. I'm on the way to getting closer to finding its maximum. What will be my next step? Anyone?
Find the derivative.
Sure. I have to find v prime, which is 18x squared minus 36x and plus 12. Good. I found the derivative. Now what?
Set it to 0.
Yes. So v prime of x undefined? No, because it's a polynomial function. And v prime of x equals 0. So I have to simply put in the graphing calculator to get those zeros. Okay. Okay, 18. Negative 18. I'm sorry, negative 36. And 12. Okay, So x equals 0.422 or x equals 1.58. Good. This is not the end. We know we have to work on this now. I'm sorry, x, I meant to write first. V prime of x and v of x. So I know x cannot be more than 3. Of course it cannot be. That's not possible. So this is 0.422 and this is 1.5800. So here is our function, our derivative right here. So I will plug in 0, positive. I will plug in 1, 18. This is 30, so that's negative. And I will plug in 10. So this will become 1800. These are too small. So I can determine these values. Of course, I don't need a 3, I don't need a 0. I can determine these values, but which of these two will give the maximum value? We already know by studying the sign of the derivative, there is only one. Anyone?
Is it 0.4?
Yes, because this is typical for a maximum. This is not typical for a maximum. This is typical for a minimum. So this is a relative min, and this is what we want for the relative and absolute max. And I will determine that value by plugging in the original volume of over there, plug in 0.422, and then I'll find the relative and absolute maximum. So 2x cubed, I want 6. I want 6x cubed minus 18 x squared and plus 12x. Again, 6x cubed minus 18x squared plus 12x, correct. So now I plug in 0.422. And I got 2.31, and that's cubic feet. So that's the reason why we can never decide based on something we get that gives a max or a minimum. This is absolutely required. You can find the second derivative, which I don't recommend, and plug this in, and then you will know if it's a maximum or a minimum. But I would never find a second derivative. If I can't find the sign of the first derivative, then finding the second derivative will be more cumbersome. Any questions on this problem? Please always write for critical numbers, showing that this is very important. You know what you're talking about. Even if both of them are nothing. As we had many situations, we had situations in which no critical numbers. If no critical numbers, no max min. If we find critical numbers, we don't know what they are, but now I do, by studying the sign of the first derivative. Very good pick. You guys are a very good example. Awesome. Good. Moving on. Let's see what else is here. Find the point on the curve y equals the square root of x that is closest to the point 3, 0. Find the points on the ellipse, such and such, that are farthest away from the point 1, 0. And we can get more and more sophisticated. Okay, so would you like to choose, or you want me to choose?
You can choose, Mayor.
Thank you for the vote of confidence. Thank you, Victoria. I'd like to choose 26, if that's okay with everyone.
That's good.
Okay, so let's look at 26. So again, can anyone summarize what are we trying to do here with these problems?
Find the max and min.
Exactly. So different situations create different functions, like what we had before. So we were given a situation with a box, and we wanted to find how big should X be in order to maximize the volume. So we found the function, we differentiated, we looked for critical numbers, we studied the sign, and now we can guarantee that 0.422 gives us the maximum volume. 1.58 gives us the minimum volume. So that's exactly what we're doing. So always the same steps. I draw a picture or a figure if I need to. Then I identify what I'm asked. That's my starting point. What am I asked to find? I'm asked to find the maximum volume, so I have to start with the volume. Okay? So now in this particular